So in this video we are going to look at one of the first great results in number theory, which is Euclid's Theorem, which states that there are infinitely many prime numbers, and we're going to prove this theorem in this video. So before we begin, let me just make sure that everyone is clear on what the definition of a prime number is. So a prime number, which will often denote p, firstly it has to be an integer, so it has to be a whole number. Secondly, it has to be a positive integer, so the negative numbers are not included in the definition of a prime number. They are not candidates for being prime numbers. And actually 0 and 1 are also excluded, so it has to be an integer that is greater than or equal to 2. 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. All of these numbers, all of these integers are going to be candidates for prime numbers. Everything to the left, 1, 0, minus 1, minus 2, minus 3, etc. downwards, all of them are not candidates for being prime numbers. And then, of course, the crucial property that makes a prime number prime is that the only things that divide it, the only integers that divide it, are going to be 1 and itself. If we're talking about positive integers, if we talk about the entire integers, then you'll also have to include negative 1 and negative of itself. So the only positive integers then that divide it are 1 and itself. So I'll write this down. The only positive integers which divide it, meaning that it can be written as that positive integer times another integer, so a multiple of our divisor makes it. The only positive integers which divide it are 1 and itself, so p. So that is the precise definition of a prime number. So you'll be familiar with the first few of them from school. So 2, for example, is a prime number because the only positive integers that divide it are 1 and 2, so 1 in itself. 3 is also a prime number because the only positive integers that divide it are 1 and 3, so itself. 4 is not a prime number because it can be written as 1 times 4, but it can also be written as 2 times 2, and 2 is not 1 or itself. So 2 is a divisor, divides 4, and it's not 1 or 4, so that contradicts 4 being a prime number. So 4 is not a prime number. Then 5 is a prime number because only 1 and 5 divide 5. 6 is not because it's 3 times 2. 7 is a prime number because it's only divisible by 1 and 7. 8 is not because it's 2 times 4. 9 is not because it's 3 times 3. 10 is not because it's 2 times 5. 11 then is the next one. 12 is not because it's 2 times 6, 13 is the next one, etc. Euclid's theorem then is that this list of prime numbers never stops. It's not a finite list, it goes on and on forever. As you go up and up in the integers, you continue to find more and more integers that satisfy this definition for being prime numbers. So there are infinite number of prime numbers. That is Euclid's theorem, and that's what we're going to prove in this video. So before we can prove Euclid's theorem, we need to prove another result that's going to then help us to prove Euclid's theorem. And the result that I want to prove is that any integer greater than or equal to 2 is going to have a prime factor. So let me write this down here. So I'll call this theorem. So statement then firstly, x is an integer and x is greater than or equal to 2. Theorem is that there will exist a prime, which I'll call p, so a prime number as we've just defined up here, such that p divides x. So this is a bit of number theory notation. This is read p divides x, and this just means that x is an integer multiple of p. So it means that there exists some m which is an integer such that x is equal to m times p. And m in this expression is allowed to be any integer, so including 1, for example. So this theorem then says that give me any positive integer x, and there must exist some prime number p such that that prime number divides your x. And we call this prime number a prime factor of x. So this is the theorem that all positive integers greater than or equal to 2 have a prime factor. And the fact that this m here, this multiple of the prime factor that's making x, is allowed to be 1, means this theorem is going to be true even for x's which are prime themselves, because if x is a prime number, then you can write it as 1 times itself, so it is its own prime factor. So we want to prove this result, and then we're going to use it to help us prove Euclid's theorem. And the way we're going to prove this is by strong induction. So we're going to start off with the base case, and our base case is going to be the case x is equal to 2, so the first number that it's going to hold true for. And then we'll do a strong inductive step where we'll assume it's true for n, or x rather, is less than or equal to some value k, between 2 and k rather, and we'll show that it would then imply that it's true for x is equal to k plus 1. So let's start off with the base case. So considering the base case, x is equal to 2. 2, of course, is a prime number, so its prime factor is going to be 2. So 2 is equal to 1 times 2, so this is your m, this is your x, and this is your p. So we can write 2 divides 2, so it is true that 2 has a prime factor, so the theorem is true for the base case. Now this inductive step, and I'm going to explain this carefully because this is a complicated, strong inductive step. So we want to assume that it's true for x is greater than or equal to 2, less than or equal to k, the integer values, so 2, 3, 4, all the way up to k, where k is some integer. We're going to assume that it's true for all of those cases, and then we want to show that if that is the case, it's also going to be true for x is equal to the next integer along. So just to show them all in line, we've got 2, 3, 4, all the way up to some integer k here. These are the ones we're assuming it's true for, and then we want to show that it means, it will imply that it's then true for the next one along, the k plus 1 integer. And if we can show that this inductive step is true, then because it's true for x is equal to 2, it will then imply that it's true for x is equal to 3, because that's the first one. You can imagine if k is equal to 2, then this list is just 2. It's not a very long list. And the next one along is 3. So it will then imply, if this is true, that it's true for 3. And then because it's true for 2 and 3, it will then imply that it's true for 4. And then because it's true for 2, 3, and 4, it will then imply that it's true for 5. 2, 3, 4, 5 will then imply it's true for 6. And then by induction, it will be true for all integers greater than or equal to 2. So we'll assume then that all of these integers do indeed have a prime factor. The theorem is true for them. And let's now prove that the next integer along, k plus 1, is also going to have a prime factor. So there are two possibilities that we need to divide it up into. Either this next integer along is itself a prime, so a prime number, in which case it can be written as 1 times itself. So 1 times k plus 1. And that is its prime factorization. It has itself as prime factor. So the theorem is true if k plus 1 is a prime. The alternative is that k plus 1 is not a prime. And if it is not a prime, then it can be written as the product of two positive integers that are strictly greater than 1. So it will have a proper, non-trivial factorization. So if it's not prime, we can write k plus 1 as a times b, where a and b are both integers and they're both strictly greater than 1. Now the other important thing to recognize about a and b is that they're also going to be strictly less than k plus 1. So a and b are going to be integers that are smaller than k plus 1. Now, this is basic multiplication facts that you're probably familiar with from school, that if you're timesing two numbers together to get another integer, two positive integers together to get another positive integer, that these ones that you're multiplying together will have to be smaller than the answer that you're getting as the product. However, if you'd like a little bit more of a proof of that, we can do this here. So we'll do a proof by contradiction. Suppose one of them was not strictly less than k plus 1. So we can choose either of them, so we'll just take b. So suppose b is the other way round, so it's greater than or equal to k plus 1. Well, we know that both of them are positive integers. That's what we've got up here. A and b are both greater than 1. So I can multiply both sides of this inequality by a because it's a positive integer, and I don't need to flip the sign of the inequality. So I'll get, therefore, that a times b is greater than or equal to a times k plus 1. Now, I also have the inequality that a is strictly greater than 1. I also know that k plus 1 itself is a positive integer, so I can now multiply both sides of this inequality, a is greater than 1, by k plus 1, and I don't have to flip the sign of the inequality. So it will become a times k plus 1 is strictly greater than k plus 1. And now we've got a problem here, because look, we've got this inequality and this inequality. This here is the same as this thing here. So this is greater than or equal to this, and this thing itself is strictly greater than that. So by transitivity, we can now conclude that, just making a bit more space, that a times b is going to be strictly greater than k plus 1, because this is greater than or equal to this, and this thing is strictly greater than this, so this one therefore must be strictly greater than this. But that's a contradiction, because a times b is equal to k plus 1, so it can't be strictly greater than k plus 1. So there is a little bit of a proof of why these two must both be strictly less than the size of this thing that they are producting together to make, if they are both positive integers that are greater than 1, which we're assuming they are. If k plus 1 is not prime, these are the things that are multiplying together to give it that are positive integers greater than 1. So a little proof there using the ordered ring properties of the integers. The important thing is that we now know that this is true, that both of them are strictly less than k plus 1. So take one of them, let's take a. A is an integer that is greater than 1 and strictly less than k plus 1. That means that it is in this set of integers that we know the prime factor theorem is true for. So a must be greater than or equal to 2 and less than or equal to k. So I know that from these two things and the fact that a has to be an integer, so it has to be one of these integers because it's bounded below by 1, it has to be strictly greater than 1, and it's bounded above by k plus 1, so it has to be one of these integers that's in between those two. So now what I can do is I can apply the fact that I've assumed the prime factor theorem is true for integers in this range, so it's going to be true for a. So a therefore is going to equal some multiple m times some prime p. And then what I can do is just substitute that in here for a. So I'll get therefore that k plus 1 is equal to m times p times b. And then just by associativity and commutativity of multiplication in the integers, I can rewrite this as m times b times p. M times b, m is an integer, b is an integer, so m times b is going to be another integer. We could just call that m prime if you like, so it's m prime times p. So here I have now found a factorization of my number k plus 1 into some integer m prime times a prime p. So k plus 1 does have a prime factor, here it is. So that then completes the inductive step. If it is true for integers between 2 and k, that they have a prime factor, it implies that it is then true that the integer k plus 1 has a prime factor. So because it is true for 2, it then implies it's true for 3. Because it's true for 2 and 3, it then implies it's true for 4. Because it's true for 2, 3 and 4, it then implies it's true for 5, and so on. You can see how this goes on forever and ever, this argument. So it's going to be true for all integers, or all integers, positive integers greater than or equal to 2, that they are going to have a prime factor. So we're now going to use this to prove Euclid's theorem. So we'll go back up here. So we want to prove that there cannot be finitely many primes. There has to instead be an infinite number of them. This list never stops. And the idea behind this is brilliant, and this is what Euclid himself came up with, and the reason the theorem's named after him. So it's a proof by contradiction. So we suppose the opposite. We suppose that there are finitely many primes. We can therefore list them. So here's the first one, P1. Here's the second one. So P1 would be 2, P2 would be 3, but we're just listing them with some abstract notation now. P3 is the third one, and then it will go on, and then there would be some biggest one that would be Pn. Now, n might be an absolutely huge number. Maybe it might be 1 million or 1 billion, but there would have to be some biggest prime number, and we'll call that Pn. Now the reason this cannot occur is consider now multiplying all of them together. So consider doing P1 times P2 times P3 all the way up to times Pn. And let me just get rid of that comma, that shouldn't be there. So we're multiplying them all together. Now because they're all positive integers, when you multiply them all together, you're going to get another positive integer. What you can then do is consider adding 1 to this and asking, what is this number's prime factor? And what we've just proven is that any positive integer that's greater than or equal to 2, which this certainly is going to be, must have a prime factor. So this thing must have a prime factor, and that's how we're going to arrive at a contradiction. So if this number were to have a prime factor, well, all of the prime numbers that exist are in this list. So they're in this product here. So it means that one of the things that's being multiplied here must be the prime factor of this. So we'll call this special prime that's somewhere inside here, we'll call that P bar. And it being this thing's prime factor means that this must equal some m, some multiple, times P bar, where m is an integer multiple. Now, what we can do is then subtract this from both sides, or add the multiplicative inverse of this if we're going in the full rigor of ring theory. But we can subtract this from both sides, and we'll then get that MP bar minus our great big product, P1, P2, P3, and P bar is somewhere in there, all the way up to Pn. And note, this is not perfect notation, because it could be that P2 is the P bar, it could be that Pn, the final one, is the P bar, but P bar has to appear somewhere in this product. That's what I'm trying to denote by this, but it's not perfect, flawless notation. I hope you'll excuse that. So this must equal 1, so all I've done is subtract this great big thing from both sides, and this is the equation that I now have true. And now what I can of course do is factor out P bar using distributivity of multiplication over addition in the integers. So that means that P bar, and we'll do a better colour than red, we'll use blue. So I can rewrite this equation as P bar times m minus, and then all the other primes that aren't P bar are still going to be in here. So again, it's not perfect notation, but you understand what I'm trying to say here. So P bar is now gone, so there's some hole there that I'll denote like this, all the way up to Pn. All the others are still there, and this must equal 1. Now, why is this nonsense? Well, m is an integer. P1 times P2 times P3 all the way up to Pn with the missing P bar there, that's still an integer. The additive inverse of this great big product is an integer. So we're adding two integers together. One is a negative one. We're going to get another integer overall. So this thing, even though how hideously complicated it looks, is just some integer. We could denote it m bar maybe. The problem with this is we've now got P bar, an integer, times m bar is equal to 1. That means that m bar must be the multiplicative inverse of P bar. It must be some integer that's multiplying with this integer to give 1, but there aren't many integers that actually have multiplicative inverses. In fact, there's only 2 of them. Only 1 and negative 1 have multiplicative inverses. 1 times 1 is equal to 1, and negative 1 times negative 1 is equal to 1. No other integer has another integer that multiplies with it to give 1. So for example, if you take 2, there is no integer that you can multiply that with that will give 1 as the answer. In the rationals, a bigger algebraic structure, of course, you can multiply it by a half, and that gives 1. But a half isn't in the integers. You have to pick a whole number, so you can pick 0, 1, negative 1, 2, negative 2, 3, negative 3, but none of those are going to do the trick. They're not going to multiply with 2 suddenly to give 1. We say that 2 has no multiplicative inverse in the integers. There is nothing that multiplies with it to give the multiplicative identity, which is 1. And in fact, in the integers, there are only two numbers that have multiplicative inverses, and they are here, written here. All the others don't have multiplicative inverses, because if you think about all the others, like 2, 3, 4, all of their multiplicative inverses in the bigger structure, the rationals, are fractions, you know, half, a third, a quarter. And for the negative ones, it's likewise negative a half, negative a third. So that means that it implies that p bar must equal 1 or negative 1, which of course it's not, because it's a prime number and the primes are all greater than or equal to 2. So this is nonsense. P bar cannot be being multiplied by some other integer to give 1. This cannot be the case. It contradicts the properties, the basic algebraic properties of the integers, that they only have two elements that have multiplicative inverses, 1 and negative 1. So that therefore means that our entire assumption that there were finitely many primes cannot have been correct, and therefore instead there must be infinitely many primes. So to finish, I'm just going to summarize this argument one final time. So Euclid's theorem is that there is infinitely many prime numbers, and the way that we prove this is by contradiction. So we suppose that it's not the case. In that case, there are going to be finitely many prime numbers, and we would be able to list them out like so. So we'd have P1, P2, P3, all the way up to some biggest one that is Pn. What we can then do is product all of these prime numbers together, like so, and of course they're all positive integers greater than or equal to 2, so when you multiply them all together, you're going to end up with another positive integer that's certainly going to be greater than or equal to 2. You then add 1 to this number, and you'll get another positive integer that again is certainly greater than or equal to 2. And then what we have already shown is that any positive integer greater than or equal to 2 is going to have a prime factor, so it can be written as m times some prime where m is an integer multiple. But this prime that it's being written as m times, that must be one of the ones that's somewhere in our list, so it must be somewhere inside this product. So we put it with this imperfect notation like so, p bar, so it's somewhere inside this product, but of course it could be one of these ones that I've already written here, but it's somewhere inside that product, is what this is supposed to be denoting. Then what we can consider doing is just basic algebraic manipulation within the ring of integers. So we can add the additive inverse of this integer, which is the product of all these primes, to both sides, and we'll then get this equation here, m times p bar minus this product is equal to 1. But then we've got p bar here and we've got p bar here. What we can do is factor that out by distributivity. So we can rewrite this like so, p bar times m minus the great big product, but with 1 missing now. P bar's missing inside there, which is what this whole is supposed to denote. But m is an integer, this great big thing is an integer, so we're just taking n and subtracting off another integer, or adding the additive inverse of this integer. That will also give you an integer, because the integers are closed under addition. So we can redenote this m bar. So we now have an equation that p bar, this prime, times another integer is equal to 1. But this is not good at all, because p bar is some positive integer that is greater than or equal to 2 by the very definition of it being a prime number. So we've got some integer that's greater than 2 suddenly being multiplied by another integer to get 1, but that's nonsense. We know that all of these positive integers, 2, 3, 4, 5, 6, 7, 8, 9, 10, they don't have multiplicative inverses in the integers. There's no integer that you can multiply them by to give you 1. They need to be multiplied by their fractions, a half, a third, a fourth, a fifth, a sixth, a seventh, etc., which aren't in the integers, they're in the rationals. So this equation is nonsense. P bar times m bar is equal to 1. There is no such integer m bar. But that all followed from this assumption that there were finitely many primes, and therefore that assumption cannot have been correct. Instead, there must be infinitely many primes. So we'll leave it there. Thank you for watching.